Mike, you got a surprise visitor.
I have a surprise visitor? Oh, that's right. Yeah, I was talking with Charlie about that moments ago. Oh, projector, will you please turn on? Yes, we are live.
We are Sony.
So.
Oh my God.
What?
Wait.
It is not you, then.
Who is that supposed to be?
Mikhail Khovanov.
Who?
Mikhail Khovanov.
You know, actually, I know Risha Khovanov.
Really?
And that is not Risha Khovanov.
Really? I guess the laser eyes are not accurate. I suppose the real.
He wears glasses?
There are glasses under there. It's kind of hard to tell with the laser eyes I put on him, but there are glasses in the photo. I will say it's also a younger photo of him. It could be, I don't know, his alter ego, I suppose.
His alter ego, Khovanov.
Yeah, so,
We might need the stock photo.
yeah.
Yeah, Khovanov.
Absolutely.
See, people don't know whether it's Khovanov Homology or Khovanov Homology.
They mix around the K's and the H. I think his half-sister put something on her website explaining why there's a K in the name, saying that whenever they go to France, people in France don't pronounce H's, and so they keep saying Ovanov, and so in order to emphasize the fact that, it's a H sound, they put the KH there to remind people it's Khovanov.
Okay.
All right. Я умею читать по-русски. Это Khovanov, не Khovanov. So, are we talking about Khovanov homology as a possible alternative to gauge theory? I mean, there's still lots of work to be done in this subject to have like a viable alternative for this, but in some areas we've seen some progress of getting the same sort of results we've seen so far in this seminar, using relatively nicer things that we can find in this homology theory. So these are the... which one? Oh, the book right there, that's Mathematical Gauge Theory by Hamilton. I didn't have a particular reason prior to choosing that book. It was just I wanted to show Khovanov destroying gauge theory with his powerful laser eyes. Although Khovanov actually didn't do this result himself. Really, it was Eun-Soo Lee who took some of Khovanov's work, and then Rasmussen took some of Lee's work to make the s-invariant, and then Picarillo took the s-invariant to come up with the thing I'm going to show you today. Am I talking too fast? I have a bad habit of doing that.
I can understand you.
Righteous. And if Ben can understand me, anyone can.
Okay, let's go.
That's mostly because I say a lot of things in class and have to repeat myself because I have a tendency to mumble. Anyways, these are the references I'll be using throughout. I also want to have a special thank you for Joe, even though he's not here, to thank him for helping me putting this together. He lent me some notes to know how to organize this thing. So, and also gave me some good resources for putting this together. All right. So first off, this is kind of like the direction that we're going. I kind of said this quickly at the beginning, but the idea is that Khovanov homology somewhat indirectly gives us something called the s-invariant, and we can use that to prove the existence of knots that are topologically sliced, but not smoothly sliced. And that construction allows us to have exotic structures on R4 without using gauge theory. So that's the direction for this talk. So first, what the heck is a slice knot? Well, the thing about knots is that they're S1, so they're the boundary of some kind of disk. And so you can take the cone over a disk, and when you put two disks together, you got a sphere. So you can imagine that if you take yourself a sphere, throw it up into the fourth dimension, and twist it up in some weird way, you can have a four-dimensional samurai slice the sphere, and the cross-section is the knot. But of course, we want this to be like a nice sphere, and so not every knot does this. In fact, the trefoil is not sliced. Trying to do this disk thing will give you a sphere that's not really embedded very well. Also, I couldn't find a real four-dimensional samurai to do this cutting, so that's a little lacking. So what do we mean by nice embedding? Well, you can mean this in two sorts of ways. One way is you could talk about topological sliceness, which means that there's a locally flat embedding into the four-ball so that the boundary of the disk is the knot in question. And we also have a smooth version of this, where it's the same story, but instead of locally flat embedding, we're talking about a smooth embedding. Questions there about these definitions?
want to give examples?
Oh yeah, that's actually where we're going next. So, two really nice examples up front is, well, the unknot. It's just a circle, and so of course it bounds a disk. But we also have the first non-trivial one that we get is what's called the stevedore knot, 6-1 in Rolfson's table. And so here I've kind of drawn what it looks like when you try to fill in that disk there. And you'll see on these little cross-section points, these are things that we could actually resolve in 4 dimensions that we wouldn't be able to do in 3. And there's even more than this. Here are all of them up to 10 crossings. And all of these happen to be topologically sliced as well as smoothly sliced. And so with this mountain of evidence, it might seem to be the case that if you have topological slice, does that implies smooth slice? That appears to be the question. And of course, you know when I ask a question like that, as Polly says, the answer is no. The answer is a resounding no. This was proved by Picarillo in 2018. You have the Conway knot, an 11 crossing knot, which is topologically sliced but not smoothly sliced. The way that she proved this was using the s-invariant, which comes from Khovanov Homology, sort of. We'll talk about how that works at the end of the talk, briefly. There's a picture of the Conway knot right there if you were curious what it looks like. I had to cheat by finding a photo online because I am not going to draw that. Anything more than 5 crossings terrifies me, and I have recurring nightmares about it.
Wait, why is it called the Conway?
John
Conway's
Conway.
drawer.
Is it easy to show that it's topologically sliced? How do they know?
I don't know exactly how they show it's topologically sliced. I was mostly focused on the part where they were checking if it was not smoothly sliced. But one of the references I listed was Picarillo's paper, and I think she addresses it in there to show that it's the case. I think the way she does it is it's hard to do it with Conway knot directly. The way the knot is kind of defies some of the conventional tools you would use. And so instead you come up with this other knot that you might call K prime. And you can show that if one is sliced, so is the other. In this other knot you come up with, you can construct using the s-invariant to get the things you want.
Okay.
It's kind of like I'm sorry if that's not a very satisfying explanation. That's my vague recollection of how this paper goes. The other nice story is that she didn't realize the significance of this proof whenever she first wrote it down. She took it as kind of like a homework exercise and told her advisor, and her advisor was like, "You did what?" and told her to publish. So a cool sort of surprise there. Okay, so why do we care? Well, the existence of these knots that are topologically sliced but not smoothly sliced allows us to construct exotic structures in R4 without appealing to gauge theory, which we'll see how to do that now. So first we need to talk about something called the knot trace. So you can take a knot here. I have another trefoil because again it's easy to draw. And what you can do is you can glue a zero-framed 2 handle along this boundary of this knot and then glue that to the boundary of a 4-ball. And this gives you a space that we're going to call xk. And this is our knot trace. And so from there, we're going to look at how these things embed into standard R4. So our first result is that if our knot is smoothly sliced, our knot is smoothly sliced if and only if its trace smoothly embeds into standard R4. So let's go the reverse direction and suppose that this knot embeds smoothly into R4. Well, since S4 is just the one-point compactification of R4, we now have an embedding from our knot trace into S4. And then we can use some properties of this ball to help us out. So the first thing is that the knot trace is compact. This is in Kowal's paper that I mentioned earlier. I won't be proving that, but we can take that as a nice fact for us. And so we can go ahead and take our knot trace and put it in one hemisphere of our 4-dimensional sphere. And the next thing we can do is that we can take the core of their 2 handle and sorry, I'm losing track of my own diagrams. Oh, sorry. The core of the two-handle is actually a disk. I mean, that's because we've taken a thickened disk and attached it to our sphere, and the center of that is going to be a disk whose boundary is the knot. And since we embed smoothly into S4, we now have this disk width boundary that kind of forces K to smoothly embed into the other hemisphere of our disk. We can kind of go ahead and loosen things on the other side. And so this means that since we have the smooth embedding in the first place, our knot here is smoothly sliced.
Can you show me X in one more time?
Yeah, sorry. I guess I'll say this whole thing is xk after we glue this two-handle to the ball.
And what is zero frame mean?
Yeah, so let's see if I can draw this on here. That was my question too when I was putting this together. I probably should have written this. I should have written this down. Ugh. So, when we go ahead and glue a two-handle into our four-dimensional space, we have our D2. What's cipher framing?
Zero.
Yes, so I'm building up to that. When we try to glue our disk, we have a place for our disk to go, but and this kind of gives us a parallel copy of the knot, and so we might be interested in how many times this copy wraps around the knot that we're gluing to. And so when we're talking about zero framing, we're saying that it wraps 0 times around the. It's kind of like a winding number of this gluing. Yes, there we go. The linking number. That's what I meant to say. Thank you, Michaela. Yeah.
Yeah, so it's cipher frame.
Yes. Does that clear that definition up? Are there more questions about this definition of the knot trace? Yes.
Is the knot trace then the whole 4-ball combined with this two-handle?
Yes. So you take the 4-ball, you glue on this two-handle. That is the knot trace.
Okay.
Are there questions about this proof here? Okay, so let's go the other direction then. So if we suppose that our knot is smoothly sliced, then that by definition means that there is some smoothly embedded disk with this knot as its boundary. And so we have kind of 2 things we can extrapolate from this fact. The first is that since S4 is the union of 2 4 balls, we can just go ahead and take this 4-ball here and glue another one on it to get S4. That'll become handy in a second. And the other thing is by the tubular neighborhood theorem, we can actually find this. We can go ahead and cross with D2, this D2 in question. We can go ahead and thicken it smoothly in 4 dimensions. So we can find D2 cross D2, our 2-handle in the space that can be smoothly embedded into D4 by the tubular neighborhood theorem. And so these 2 things together gives us that our knot trace smoothly embeds into S4 because we have our we've taken our knot, we've glued the disk to it, and we've done so smoothly, and so that's how we get that there. And we can get that from R4 because since S4 is the 1-point compactification of R4, we take a point away, so now we have our smooth embedding into R4. So our knot is smoothly sliced if and only if its trace smoothly embeds into R4. Questions about this proof here?
Can I see the definition of SK again? Sorry.
Yes, sorry. It is a little weird. I will acknowledge that. So, you just want to see it, or do you want me to like walk through the construction again?
So you're saying XK is a copy of D press?
No. So XK is you take your 4-ball and you can imagine you're not living in the boundary of this ball, and so from there you want to glue a 2-handle onto this knot in the boundary of the sphere. Sorry. Yes.
So it's a copy of D4.
D2 cross D2.
Attached to
So
Right.
the-
Attach a
that's
D4
the
along
tubular
the,
neighborhood you have.
Say that again, I didn't quite hear you.
That's the tubular neighborhood.
That's the tubular neighborhood, yeah, that we want to use in the second part of the proof.
how many boundary components XK have?
That's a good question. I don't know the answer to how many boundary components it has.
Then you're gonna attach like
Is that the boundary of D4?
D4?
Say what?
Shouldn't it just have one boundary component?
Yeah, I believe so, yeah, because the boundary is just S3 and we're gluing something along S3 and doing so. It's attaching a handle, really, so it should, I don't think it should add another boundary component.
You're attaching on one D2, but the boundary of D2 cross D2 as well.
It's the solid torus, isn't it?
It's two different solid tori.
Two different solid tori. And that's why we also need the framings to specify how these tori glue in exactly.
D2 cross D2. Well, D2 cross D2 is D4. So the boundary of D2 cross D2 is.
S3. S3. Oh yeah, because the Haggard splitting of.
But then the product structure gives you the standard Haggard splitting of genus 1, which is what this is.
Gotcha. Thank you.
You know, I don't know everything, but what I think is the reason why they're called slice knots is exactly what you showed, that it's a slice knot.
Yeah, the samurai.
It's called a slice knot because if you have a knotted two-sphere in R4, then when you slice it with an R3, the knot you get is a slice knot. And I think that's what you were proving, that if it's a slice knot, you can see it as a slice of a knotted two-sphere in R4. I think that's what you just proved.
Yes, it is, absolutely. Thank you, Charlie. Are we good to move forward to the next result we're going to use? This next one is that if K is topologically sliced, then its trace admits a locally flat topological embedding. As it turns out, the proof is exactly the same as above. You really just replace the word smooth with locally flat, and you replace smoothly sliced with topologically sliced. You also, now technically there's a bit more to that than I'm kind of sweeping under the rug here, because tubular neighborhood theorem is definitely a smooth manifold sort of thing. But you can apply a locally flat version to make everything check out, and it's all hunky-dory. That's a fun word. Sorry?
What is a locally flat embedding?
I'm glad you asked. A locally flat embedding. So the picture of it, anyways, is if you have, is your Rn space here, and you have one third subspace would be like another lower dimensional real space, so like some line in here, or I guess maybe not. That's the one I want. Just like this line here, right? So it kind of sits flat inside the space here. Well, what you can do is that you can have some manifold here with some submanifold, this pair here. So there's like a local homeomorphism that sends it to this sort of pair here. Like the manifold is locally Rn, and the submanifold is locally this line in here that sits flat inside. It sits nicely in your manifold without poking and prodding and twisting too much.
Do you always want it to be the x-axis, or is that just...
That's just a nice... I think it doesn't need to be that way exactly. I just chose it because it's nice.
So maybe it's an analog of a regular submanifold rather than the
Yeah.
but maybe not with the smoothness condition.
Without the smooth... Yeah, exactly. It's the best you can get in the topological setting. So now that we have these things, if K is topologically sliced but not smoothly sliced, we can construct exotic R4. So the construction is as follows. So first, we suppose such a knot exists. I haven't shown you yet, other than just saying that someone proved it. But let's pretend that's a thing we know. Well, then, by definition, that means that we have a locally flat embedding into R4. And what we can do is that we can create some new manifold that is the complement of the interior of this knot trace. And again, another fact I'm going to appeal to but not prove because that's beyond the time and patience we have for this allotted time, is that any non-compact connected four manifold admits a smooth structure. And as it turns out, this thing is definitely non-compact and it's connected and it's a four manifold, so it has a smooth structure. Yay! So we equip M with such a smooth structure. And the first thing to note is that the boundary of M is 1, homeomorphic to our knot trace, and 3 manifolds have a unique smooth structure. So what we can do then is that we can glue back xk into it. That will have some smooth structure given to it by the smooth structure on the boundary. But k is not smoothly sliced. And so what that tells us is that the resulting manifold is homeomorphic to R4, but it can't be diffeomorphic to it. Otherwise, we'd have a smooth embedding, but that contradicts our thing about the knot trace smoothly embedding if and only if the knot is smoothly sliced. So there we go, a non-gauge theory proof that of the existence of exotic structures on R4.
I kind of missed the part where you showed it's connected. Are you just going off the fact that it took a disk?
I didn't hear the last part.
Why are you arguing that M is going to end up being connected?
Oh, that's true.
I mean,
Proof by it feels true and haven't had the time to check it myself, but someone smarter than myself proved it. This is in Jamal's paper, that Kovac's paper, going into detail about non-compactness and connectedness.
Sure. I mean, non-compact is something I can get. Connected
Sure.
was something I thought that.
That one is a little dicey. I guess the idea is like a... Actually, no, that isn't necessarily true. Are there any other questions about this construction?
Maybe you can scroll up and down again just so I can see what we're...
Sure.
Okay.
By the way, how is this box and arrow notation work for you all? I know it's it can be a little confusing. You haven't seen me do this before, but also I feel like it's better than that wall of text.
Good. It's good.
Okay, cool. It's something I first developed to help philosophy students I was tutoring to understand how arguments flow, and sometimes I do it without explaining what's going on with the boxes and stuff. Okay. Now we get into the s-invariant. This is the part where I admit that I don't really understand entirely what's going on, but I'll try my best to explain the story so far with this. So first, we need to understand what Khovanov homology is. Getting into actually defining this will take probably another hour or so, but if you want to actually read exactly how this works out, I recommend this paper down here in purple on Khovanov's categorification of the Jones polynomial. George Barnaton actually just does a lot of nice stuff on this thing. He draws a lot of good pictures and is very thorough in his explanations. Unlike what you see in most topology papers, where it's either too many pictures and not enough rigor, or too much rigor and not enough pictures, and so either way you can't understand what's going on. But he does a great job. The idea here is that you can build these cubes of smoothings of your knot. So you look at these little crossings and you have what's called a 0 smoothing or a 1 smoothing. And you get these sorts of blobs going on here with these maps M and delta. The idea about when to know to use M or delta is that if you go from more blobs to fewer blobs, you're going to use M. I like to think of that as merging. Really it's multiplication, but merge is more fun to say. And if you go from fewer blobs to more blobs, you can think of them as dividing, or delta, or co-multiplication actually, but that's the idea here. These maps are defined down here. Oh yeah, also I should mention that you can associate vector spaces to all of these smoothings. But the point is when you do that, these vector spaces combined with what happens when you take the sum of all these linear maps gives you a chain complex that you can do homology, well, cohomology actually, but you can do cohomological stuff with it. And so who cares? Well, this categorifies the Jones polynomial. If you take the graded Euler characteristic in this homology theory, out falls out the unnormalized Jones polynomial. And so since homology is more general than Euler characteristic, the idea is that maybe we can find more stuff about knots from this machinery. Good so far? Very high level explanation. I understand entirely if you're like Merrick. We're just smiling and nodding. So next, Ainsley comes up with this thing where you just take endomorphisms of this Khovanov homology stuff, and then the result of this is that you get these new maps for M and delta. And so you do the same game, but with these linear maps instead. And so you get a slightly different, slightly more generalized version of Khovanov homology. And then from that, Jacob Rasmussen does some alchemy with spectral sequences, where you can do these spectral sequences on the Lie homology, and that allows you to find these things called S-min and S-max. I don't actually understand what these are. I just know that they are a thing because...
Are they not?
They're not knots. They're numbers associated to your knot. Good question. I probably should specify that these are numbers. And then you can go ahead and take the average of these things, and that's the S-invariant.
So they seem like they're some kind of eigenvalue, and I'm very skeptical. But,
yeah, I failed to write down the paper where Rasmussen does this. I apologize.
It's a short and sweet.
It is short and sweet. I just don't have the palette for it quite yet. Maybe this summer I'll read it again with more patience, so I could really understand what the S-invariant is. Oh, go up to Lie homology, or...
Can you compare these two M and delta with the original?
Absolutely. Let's see if I can grab these and move them. And so, is that what you wanted, so you can compare them side by side?
Oh, thank you.
The main thing that changes is that, well, one,
the minus.
yeah, this thing changes, and also we set it to where these two give the same result, whereas previously they gave different ones. So just those three changes.
It's more symmetric.
Yes, it's more symmetric. Yes.
Is this like better?
Well, it actually sort of collapses, is what happens. So it's, and then the S-invariant is related to how it collapses.
What do you mean like collapse? Like it doesn't work for certain people?
Khovanov homology is bigraded, okay? And then what happens is everything that lies on certain diagonals gets collapsed, and so the Lie homology is monograded.
In some sense, simpler.
And then I think what the S comes from is there's a filtration.
So,
Yes.
so the Lie
There's
homology
filtration.
is two-dimensional. And it consists of two things in some logical degree, and they have associated Q gradings too. And the Q gradings that they have are the S-min and S-max.
Okay.
And so if you take the average of the two numbers, the only information that is contained in Lie homology, that's the S-invariant.
Whereas Khovanov homology doesn't have a Q grading.
It does have Q grading, but it's actually really big.
Oh.
It can be like quite
Okay.
complicated.
Okay.
And what this change does is destroy everything besides one number,
Oh.
for a knot at least.
So it's
But
less,
later it's a little more complicated.
less fine. but
Well, a
then
lever,
actually
you pull it and
work
use
with
it.
Well,
Yeah.
what you do is you keep track of how it's falling apart.
Sure.
Okay, that's the spectral sequence thing I was talking about that I wasn't quite parsing. So yeah, that's what we got there with the S-invariant. And so what Picarillo does is, so we have our Conway knot, and what we can do is that we can construct this other knot K prime, because the regular old Conway knot is a little bit messy in ways we don't like. And what we can show is that this knot is smoothly sliced if and only if K prime is smoothly sliced. And so you work with this other knot instead. And you show that this one is not sliced because it's, when you do the S-invariant of this knot, it's not 0. There's other result you can show that it's sliced if and only if the, is it if and only if, or it's just, no, it's not if and only if, it's only one direction. If it is sliced, then it's s-invariant is 0. So if it's not 0, then it's not slice.
Maybe you can say how the s-invariant is related to this genus or something.
I only vaguely understand how it's related to genus. So like this table that I constructed, or this list of knots I had earlier that were that are topologically sliced but not smoothly sliced. So you go into knot info, where all grade knot information is found. There is not a button to select topological slice or smoothly sliced, but instead there are buttons for where they're talking about their 40 genus and equal to 0. And so there's a smooth version and a topological version. And so what you do is you look at the table where that genus is equal to 0. And I'm guessing that s-invariant picks up on that genus. And so if
yeah, so the s-invariant is a lower bound.
It's a lower bound.
Four-ball genus.
Mm-hmm.
So,
oh yeah, that's right. I have this written up in the title thing very sneakily.
oh, so that's the reason why if it's not 0, then it's not slice. Right?
Yes, that's right. Otherwise it'll be, yes. If only I'd paid attention to what I wrote.
Well, it's hard with Michael's eyes.
I think you need -1.
I need a what? 2g minus 1. Oh, thank you.
Maybe not. No, I don't think so. Sorry. We don't need.
We don't? Okay, cool. Let's see.
There was an invariant similar to this derived from Hagar.
The tower.
The tau
Yes.
invariant, and that's why it's S as opposed. That's because it's next to T.
And I believe Barnett's on had like a list of sort of properties you can get with Khovanov homology, and there's one that he called S, which satisfies certain things, and Rasmussen thought that his thing was kind of similar to Barnetton's s-invariant. They're not the same, but they have some similar properties, and so that was another motivation for choosing S specifically and not some other Greek letter like upsilon or something.
His name is Rasmussen, which starts with RST. So
RST.
You interpolate S is in the middle. What he did because it was S in time.
So that's everything I wanted to share with you. I can go back if there are things you'd like to see again.
It's brave.
Thank you.
So there's a famous result.